Closely at these blades, we see that some blades are in stationary rows attached to the case. These are called stators. Other blades are in rows attached to the rotor assembly. When the rotor assembly rotates, these blades move much like a fan. These blades are the rotors. Small amounts of compression occur between each set of rotors and stators. Each pair of rotors and stators is a stage, and this compressor has 11 stages. At each stage, the rotors speed the air up and the stators slow it down. In slowing the air's velocity, the energy from velocity is transformed into a slight increase in pressure. While the velocity of air remains almost steady, the pressure is increasing as it passes through each stage. Each stage multiplies the pressure obtained from the preceding stage. A very small pressure in the first stages quickly becomes a very high pressure by the last stage. Remember that the air path decreases in size along the compressor's length. This permits the compressor stages to maintain the pressure passed along from the previous stage. Now, with an increase in pressure goes a similar increase in temperature. So the air leaving the compressor has gained high pressure and a high temperature. This is done by alternately speeding up and slowing down the air in an ever-decreasing volume of air path.
The question you may be asking yourself is, how does air movement get changed into pressure? The answer is related to the shape of each compressor blade. Each blade is shaped like an airplane wing or airfoil.
In the airfoil, air flowing over the top must travel over a longer path in the same time as the air on the bottom. To do this, the top airflow must increase its velocity. You recall that when velocity increases, pressure drops. This is how a low pressure above the foil and higher pressure below is obtained. This difference in pressure creates a lifting force that pushes the airfoil towards the low pressure area.
Now let's look at the compressor blades again. At the first stage rotor, a low pressure area is created on this curved surface as the rotor rotates. Air from the atmosphere then rushes in to fill this spot.
The rotor blade motion increases the air velocity and moves the air into the spaces between the next set of stator blades. Now, whenever air is forced through an enlarging air path, the velocity decreases while the pressure rises. It's at this point, in the spaces between stator blades, where air is slowed down and we gain air pressure. This is called diffusion, and it is the key principle which makes the compressor work. The space between rotor blades acts as a diffuser too, slowing the air velocity. Won't the air eventually stop if we keep slowing it down? No, it won't stop because two things are occurring which maintain air velocity. First, the moving rotor blades add energy to the air and force it along to the adjacent stators. You remember that the air path along the compressor's length is decreasing in volume. Let's look very closely at the space between one set of rotors and stators. Here, the shape of the air path is decreasing. In fact, we have a miniature nozzle. This causes the velocity to rise slightly before the air enters the next set of blades. So the nozzle effect is the second way that air velocity is maintained. As the air moves between hundreds of blades on 11 stages, its pressure is multiplied by diffusion and its velocity rises and falls in the process. After leaving the compressor, another pressure rise occurs before the air reaches the combustor. The pathway the air follows is shaped like a diffuser. The diffusion path increases in area and the air velocity slows down so combustion can occur. It is in this diffusion pathway that the final pressure increase occurs. This diffuser pathway is formed by the diffuser case, the compressor bearing support housing, and the turbine bearing support housing. At the rear of the diffuser, air pressure is the highest in the engine. Since this pressure is most important in monitoring engine performance, it's given a special name, the compressor discharge pressure, or abbreviated in engineering terms, PCD. PCD is measured at the turbine bearing support housing and is an important display on the engine gauge panel.
Here's a brief review of what you've learned. The basic features of the compressor include rotors, rows of moving blades, stators, rows of stationary blades, air path, decreasing size forward to aft, axial flow, airflow parallel to the compressor rotor axis. In the compressor, air velocity remains constant. Air pressure increases. Air volume decreases. Air temperature increases. Diffusion is the principle of increasing air pressure by forcing air through an expanding pathway. Air velocity is maintained by energy from moving rotor blades, nozzle effect between rotors and stators. The term PCD refers to compressor discharge pressure. It is measured at the aft end of the diffuser in the turbine bearing support housing. The compression of the air plays an important role in producing power. The design of the compressor permits large quantities of air to be compressed into an exceedingly small volume, both to sustain and cool combustion. Diffusion, the key to compression, occurs throughout the compressor. The result is the delivery of high-pressure air to the combustor without any significant loss in airflow. This is Lesson 4, Compressor Stall. Before moving on to other engine sections, the compressor operation must be explained further. In the previous lesson, you learned how the compressor functioned at normal operating speeds. At lower speeds, however, the process of compression is not nearly so perfect. If not carefully controlled, it can result in failure of the compressor to pressurize air. This condition is called stall. This lesson will investigate the causes of stall and how it is prevented. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Explain the term stall. 2. Describe how stall is prevented. To introduce this lesson, here is your instructor, Don Lovejoy.
In the previous lesson, you saw how the compressor was able to compress air while maintaining a constant airflow velocity.
When the engine is running at normal operating speed, the stages are matched perfectly to accept the compressed air, multiply the pressure by a small amount, then pass the air to the next stage. But at lower speeds, the stages are not matched. The forward stages produce more airflow than the rear stages can handle. The rear stages become temporarily blocked, unable to move the large volume of air out of the compressor. The flow velocity drops, causing a stall condition. Let's use the airfoil to explain low-speed stall. The airfoil is designed to affect airflow to form a pressure differential across the foil which creates lift. There are three factors which affect the performance of the airfoil: its velocity, its shape, and the angle the foil meets the air.
If the angle the foil meets the air becomes too great, the low pressure area begins to draw air back down onto the foil. This turbulent air condition upsets the smooth flow of air and destroys the low pressure area, which causes a loss of lift. When this happens, stall has occurred. In an airplane, stall makes the airfoil inefficient and lift is lost. When stall occurs throughout the compressor, airflow ceases. This condition is known as surge.
When airflow decreases in the turbine engine, the combustor and turbine sections heat up rapidly to extremely dangerous levels. This will severely affect the turbine components and decrease the engine's lifetime.
Remember that stall occurs at lower speeds, where the forward stages are more efficient than the rear stages, and air piles up in the rear stages. Since each rotor blade is an airfoil, stall occurs on each rotor blade.
Let's look what happens to the angle of air meeting the foil as the air velocity drops. Using vector diagrams, here's the direction and speed of the forward stage rotor blade. We'll call this vector A. And here is the incoming air. Vector B shows its direction and speed. The resulting angle of air meeting the rotor is vector C. This, of course, is the ideal situation, where air meets the blade at the angle the blade is designed for. But while the forward stages are pushing air to the rear stages aren't able to move it on rapidly. Here's the result. Vector A is now the direction and speed of the rotor blade. But the airflow has slowed down due to blockage in the rear stages. Here's vector B again, with its velocity component shorter than before, representing a drop in airflow speed. Here's the resulting relative speed and direction of airflow on the blades. Vector C meets the airfoil at an increased angle because air velocity has been reduced to half. If the rear stages continue to choke and the air velocity drops very low, it's easy to see what happens. Though the blades continue to rotate at the same speed, the airflow almost stops. Here, vector B represents very low air velocity. The relative angle of air meeting foil is so great that turbulence develops. And that important low-pressure area over the foil is destroyed.
Earlier you saw how the forward stages are perfectly matched to the rear stages at normal operating speeds. It's at lower speeds that the forward stages outperform the rear stages and stall occurs.
To prevent stall at low speeds, the compressor reduces the amount of air which enters the first three rotor stages. This is done by changing the direction of airflow meeting the forward stage rotors and stators. The first stage rotor has a speed and direction shown by vector A. The inlet guide vane can direct incoming air at a new angle. Vector B shows the new angle. Its length is unchanged from before because the velocity of incoming air remains high. You see both the relative angle and velocity of incoming air are reduced, shown here by resulting vector C. By controlling the angle at which air enters the first three stages, a stall condition is avoided during the start cycle.
The inlet guide vanes, the first stage stators, and the second stage stators are movable and change the angle of the air entering the first, second, and third stage rotor assemblies. At low speeds, this reduces the volume flow rate in the forward end of the compressor enough to allow the rear stage of the compressor to move the air without choking and causing a stall condition. The inlet guide vanes and stator assemblies are adjusted automatically with increasing speed during the start cycle to match the forward and rear end of the compressor at all times.
Here's a review of what you've learned. Stall is a low-speed compressor condition caused by forward stages producing too great an airflow, rear stages